Guys, let's start with today's lecture. Today we are going to study about a transpose and a LU decomposition. Now let's first start with transpose of a matrix. We have already studied in high school what a transpose of a matrix is. So if I take any matrix and if I take either the rows and the columns and then swap it into the rows, then the resultant matrix is known as the transpose of a matrix. So if I have denoted this with A, where this is of order m cross n, then our resultant matrix is going to be of order n cross m, right? And if I have denoted each entry with the aij, where I is the number of rows and j is the number of columns, then each entry in the transpose is denoted with the AJI, right? So that is what transpose of a matrix is. Now the next are the properties. While the addition our transpose is distributed, so I can either take the resultant and then transpose them together, or I can either transpose them and then add the resultant. Okay, now the next is for the product of two matrices. So in this they basically swap the position and then transpose them and then multiply them together. So to understand this, let's first take an example of AX ka transpose. So we have already studied what what the multiplication of A dot X gives. So if A is any matrix and X is any vector, so AX is basically the combination of columns of A, right? And with its transpose, it gives us the combination of rows of A transpose. So while A works on the columns of A, its transpose works on the rows of A transpose. So it is basically the same combination of the vectors, because here we are working on the columns of A, here we are working on the rows of A transpose, which are basically the columns of A only. So AX is the combination of columns of A, while its transpose is the combination of rows of A transpose. Okay, so the next our next topic is a symmetric matrix. Okay, so what a symmetric matrix is: the matrix is said to be symmetric when it is symmetric around its main diagonal. So this is known as our main diagonal, and these are our off diagonal entries. So when it is symmetric around its main diagonal, then the matrices are said to be symmetric. This means that if you flip the matrix around its main diagonal, the matrix remains unchanged, it doesn't change. And how do we verify it? We verify it through this equation. When the transpose of a matrix is equal to the matrix itself, then the matrices is known as the symmetric matrix. Now one key property of a symmetric matrix is that if our A is symmetric, then our inverse is also symmetric. Okay, so if our A is symmetric, and its inverse is possible, we will study later that not every matrix can have an inverse. So if its inverse is possible, then that matrix will also be symmetric. Okay, so one key property that you have observed here is that this is the property of a square matrix only. That means our rectangular matrix cannot be symmetric. So if I want to generate a symmetric matrix through any matrix, that is also possible, where we can take any matrix, rectangular matrix R of any order m cross n, it could be of any order, and I can produce symmetric matrices with that. How do we do so? How do we do that? We basically take R and then we multiply it with the transpose of the matrix, and the resultant comes out to be symmetric. So this matrix is always symmetric. So that is how we produce a symmetric matrix. Okay. Earlier in our previous lectures, we studied what LU decomposition was, right? So if I am given any matrix A, square matrix A, so I can decompose it or factorize it into L and U, where L is our lower triangular matrix and our U is our upper triangular matrix. We have already studied that, right? So in this, what we first observe, what our first observation is that in our lower triangular matrix, our diagonal entries are 1. Now why is that so? Because we did the elementary operation on the off diagonal entries only. So we operated here and here to produce the pivots to make right? So that is why our diagonal entries are 1. Now in our upper triangular matrix, our diagonal entries are our pivots only, right? So here you will see that although these are non-zero entries, they are still unsymmetric. Unsymmetric not in the literal sense that it is unsymmetric, but in the sense that our diagonal entries are not 1. So so we can further factorize or we can split our U into D, that is the diagonal matrix, and U, which is modified of our previous upper triangular matrix. So we can take our upper triangular matrix and then modify it into more symmetric form, where here our diagonal entries are 1, and we have how did we produce that? We basically multiplied each row with its pivot, and the resultant is modified U, and in multiplication is the diagonal matrix, right? So the factorization can be written from A equals to LU and A equals to LDU. Now why is that important? Because it basically plays a very important role when our matrix is symmetric. So let's assume that my matrix is symmetric, right? I'm going to take the previous example only, where my A is symmetric. So first I have factorized it into L and U. So this is my L and this is my U matrix. Now if I further decompose it into the triple L, D and U, where this is my diagonal matrix of 1 comma 3 and this is my U. So here one thing you are going to observe here is that my U is basically the transpose of a lower triangular matrix only. Now this is not a usual case with every matrix. This is only possible when our matrix is symmetric. So when our matrix is symmetric and we further decompose it into LDU form, then the modified U is basically the transpose of the lower triangular matrix only. Okay, so what it basically does for us is that it makes the elimination a lot faster. So the work of elimination is cut in half, and that is why this factorization is preferred. So what are the pros of symmetric matrices? That the elimination is faster, it makes the matrix work in half, and there is symmetry in the triple product. Okay, so that is it for today. This was a very short lecture where we only covered the transpose and the symmetric matrix. Okay, I hope you liked it. Thank you.